Hello class, welcome to the Stat 511 Week 11 video on the inferences of two means. So our objectives for this class are to focus on the hypothesis test and confidence intervals for the differences between two population means. Now there are three cases for this. Case 1, when we have population variances are known. Case 2, when the population variances are unknown but assumed equal. And third, when the population variances are unknown but assumed unequal. So objective 1, we're going to be conducting the hypothesis test for the differences in two population means. Now, first, before when we were doing a one sample z-test or a one sample t-test, we compared this to a population mean of one sample to a fixed value of mu naught. Now we're going to want to compare the means of a quantitative variable from two different populations. Couple examples, say the mean resting heart rate for men compared to the mean heart rate for women, or maybe the mean cholesterol level for people who are taking drug A versus the mean for people who are taking drug B. So when we're comparing two means, we are going to have two populations of interest. And from these two populations, we are going to draw two independent samples, one from each population. From there, we will compare, ideally, the averages of these two populations. We may or may not know the population variances or population standard deviations from the two populations. If we do know our two population standard deviations, we'll do our two sample z-test. If we don't know, then we'll do a two sample t-test. So let's recall the steps for hypothesis testing. Step 1, we'll state our hypothesis in acceptable alpha level, then specify the model and check the assumptions. Step 2, we'll calculate the test statistic. Step 3, define the rejection region and make a statistical decision. And then step 4, we'll state our conclusion in the context of the problem. So regardless of the situation, we'll begin step 1 the same. Independent sample assumptions. We have three assumptions of interest. First, that each sample is a random sample. 2, the samples are independent. And 3, each population of responses has a normal distribution. To do this, we must use two QQ plots to test this assumption, one for each sample. If the assumption is not satisfied for either sample or both, the inference will still be valid if the central limit theorem can be applied, meaning we have sufficiently large sample size. Now let's also consider writing our hypothesis, still looking at step 1. Our parameter of interest will be mu1 minus mu2. That is the difference of population average 1 minus the average population 2. Most commonly, our null hypothesis will be written as mu1 minus mu2 equals some delta naught. In general, for this class, delta naught will be equal to 0. The only exception is if the problem expresses an established known difference. So, for example, we talked before about the resting heart rates for males and females. Well, perhaps there's a known average difference that hypothetically that men have a resting heart rate 5 beats more than women. And we're trying to establish if that difference has changed from the 5 beats. And so what it might then be is mu1 minus mu2 equals 5, where mu1 is the males and mu2 is females. And we're trying to see if that difference has changed. But if we have no established difference, which is going to be the case probably 90% of the time you do these problems, then your mu naught will be equal to 0. Your alternative hypothesis can be one-sided or two-sided. You're still going to see that same not equal to, greater than, or less than. And again, that same hypothesized value, most often it will be 0. So at this point, step 1 for all 3 cases is the same. Now we can start looking at step 2, where the cases are going to be different. So from here, we're going to break this up to 3 sub-objectives to examine each case individually. So case 1 is when we have the known population variances. And so for this case, our test statistic will be z equal to our sample mean 1 minus sample mean 2 minus that hypothesized difference all over the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And we know that this statistic has the normal distribution with mean mu1 minus mu2 and variance sigma 1 squared over n1 plus sigma 2 squared over n2, meaning we will compare this to the normal distribution. So for our step 3, if we decide to go with the critical region method, then we can use that if our alternative hypothesis is less than, then we will reject the null hypothesis if z is less than negative z alpha. We will use the reject the null hypothesis in the two-sided situation if the absolute value of z is greater than z alpha over 2. And in the one-sided case that is greater than, then we'll reject the null hypothesis if z is greater than z alpha. Otherwise, we will fail to reject the null hypothesis. If we decide to use the p-value method, we will still follow the same two-sided rules for calculating the p-value. If we are in the less than case, then our p-value will be the probability of z less than or equal to our test statistic. In the two-sided case, our p-value will be 2 times the probability of z being greater than or equal to our test statistic, the absolute value of our test statistic. And in the greater than case, our p-value will be equal to the probability of z being greater than or equal to our test statistic. And we will always reject the null hypothesis if p is less than or equal to our alpha value. Otherwise, we fail to reject the null hypothesis. And our step 4 is going to be the exact same. It is consistent. If we reject the null hypothesis, then at the alpha level of significance, we do have sufficient evidence to say that the alternative hypothesis is true. And if we do not reject the null hypothesis, then we can say that at the alpha level of significance, we do not have sufficient evidence to say that the alternative hypothesis is true. And remember, our alternative hypothesis is talking about 2 population means. So you might be saying phrases like we do have sufficient evidence to say that the, population mean average heart rate for males is greater than the mean population heart rate for females, something like that. So that's the end of our case 1. Now let's examine case 2, where our variances are unknown but assumed to be equal. Remember, in case 2 and 3, we'll be using the t-distribution. So our t-statistic will be t equal to our y1 bar minus y2 bar, meaning our 2 sample means subtracted from each other, all divided by the square root of a pooled variance statistic that we do need to calculate, multiplied by the quantity of 1 over n1 plus 1 over n2. And that pooled variance statistic is as follows: the quantity of n1 minus 1 multiplied by the sample variance of sample 1 plus the quantity of n2 minus 1 multiplied by the sample variance of sample 2 all over n1 plus n2 minus 2. And this is going to, as I've said before, follow the t-distribution, but with degrees of freedom n1 plus n2 minus 2. And I do realize 2 typos, one I corrected already. And also this really should be the sample mean 1 minus sample mean 2 minus that hypothesized value. Again, this is pretty much always 0. So we generally can ignore the thought of that. As for step 3, making our decision, since this does follow the t-distribution, we can still follow those same rules. I apologize for these mini typos. I copied and pasted from the previous slides for this part, and so I forgot to change a couple little things. I will change them before I post the lecture, but obviously the videos will have these minor little typos. So when we are doing the alternative hypothesis for less than, then we will reject the null hypothesis if t is less than negative t alpha. If we're doing the two-sided case, then we'll reject the null hypothesis if the absolute value of t is greater than t alpha over 2. And if we're doing the one-sided case where we're saying strictly greater than, then we will reject the null hypothesis if t is greater than t alpha. And of course, otherwise, we will fail to reject our null hypothesis. As we've established in previous lectures, we can't get an exact p-value when working with the t-distributions, so I've only given us the critical region method in these cases. Step 4 is exactly the same as previously mentioned. Remember, if we reject the null hypothesis, we do have sufficient evidence, and if we fail to reject the null hypothesis, we do not have sufficient evidence. This brings us to our third objective, not really our third objective, but our third part of objective 1, case 3, when we do not know our population variances, but we assume they are unequal. And once again, these do follow the t-distribution. This time our test statistic t is going to be equal to our sample mean 1 minus our sample mean 2 all over the square root of our sample variance for sample 1 over our sample size of sample 1 plus our sample variance from sample 2 over our sample size from sample 2. And the calculation of the degrees of freedom is rather complicated. It's this statistic right here. Be very careful when you're typing this into your calculators. What I would recommend is I would actually type in the degrees of freedom for the pooled case, that n1 plus n2 minus 2. It's not going to be the exact degrees of freedom, but it isn't usually horribly far off. And the reason I would tell you to calculate that first is because it's quick and it'll give you an idea if your calculation is reasonable. That is not a necessary step, that n1 plus n2 minus 2. It's just a piece of advice that I've noticed over doing this calculation multiple times by hand, is that it's easy to make a mistake and it's good to be able to tell the reasonableness of your degrees of freedom. Once again, we can still use the same critical region method with the t-distribution with our one-sided and two-sided test. Since I did just go over it a few seconds ago, I will not go over it a second time. And our step 4 will also be the exact same thing. And just again, this one I will repeat. Remember, if you reject the null hypothesis, you do have sufficient evidence. If you do not reject the null hypothesis, you do not have sufficient evidence. That is very important. Okay, looking at example 1, a total of 38 college freshmen were administered the Survey of Study Habits and Attitudes, the SSHA, a psychological test designed to measure motivation and attitude towards study habits in college students. We were given the following summary statistics. We were given the scores for females and males, each with their sample size, mean, and standard deviation. Because it didn't explicitly state that this was the population standard deviation, it's safe to assume that this is the sample standard deviation, particularly that it says sample statistics. And so the school administrators are interested in whether the population mean score for females is higher than the population mean score for males. We're going to let alpha equal 0.05, and we are going to assume equal population variances. Okay, so at this point, we can define our parameters and say, let mu1 be the population mean SSHA score for females, and let mu2 equal the population mean SSHA score for males. So this is going to tell us that our hypothesis, based on our previous side, is going to be mu1 minus mu2 equals 0 for the null hypothesis, and the alternative hypothesis will be mu1 minus mu2 greater than 0. Now we can check our assumptions. It was stated that each sample is a random sample. We can, although it wasn't stated explicitly, but whenever we see random, we generally understand it to be independent, meaning that each sample was independent of each other, or each observation was independent of each other, I should say. And we want to know if each population of responses had a normal distribution, meaning where the SSHA score is normally distributed in the population of females and also for males. Now, this is not something that I'm going to have you required to do by hand, but what will occur is that I may give you the QQ plots for these two populations and ask you if the assumption holds. Which examining these cases, I would say that these populations are normal enough for us to say that the normality assumption holds. Is the male score as ideal as I'd like it to be? No, but overall, it does stay pretty close to the line. And while we do have a dip here, we also have a dip here, so it's not strictly above the line or below the line. So like I said, I'm going to say it's normal enough. And this is particularly true when we work with real data. So now we can continue with our hypothesis testing. So just to recall, our null hypothesis is mu1 minus mu2 equal to 0, with the alternative being mu1 minus mu2 greater than 0. We were given N1 is equal to 18. Our sample mean was 141.05556. And our sample standard deviation for sample 1 was 26.436321. For our population 2, we had our sample 2 statistics were N2 equal to 20. Our sample mean was 121.25. And our sample 2 sample variance was 32.851941. And we were told that, our significance level was 0.05. Now, because we were not given the population variances, that means we're already examining case 2 or 3. We were told to assume that the population variances, although unknown, are equal. So this tells me we're going to be using the case 2, or the pooled variance case. So to start off then, it will be necessary to calculate our pooled variance statistic, which is SP squared. And so to plug in our values, this would become 18 minus 1, 26.436321 squared, plus 20 minus 1, and quantity multiplied by 32.851941 squared, all divided by 18 plus 20 minus 2. And if I type that into my calculator, I'm going to get something approximately 899.63. Now we can calculate our test statistic, where t is going to be equal to 141.055556 minus 121.25. No established difference was given to us, so we do just leave it as that. So our two sample means subtracted, all divided by the square root of our pooled variance. So 899.63 multiplied by 1 over 18 plus 1 over 20. And if we type this all into our calculators, we are going to get a test statistic of 2.03. And so now at this point, we can move on to our third step, whereas we will reject our null hypothesis if t is greater than t alpha. Remember, we were given an alpha value of 0.05. We also need our degrees of freedom, which in this case is n1 plus n2 minus 2. And so this is going to give us degrees of freedom of 36. We now need to use our t-table to get our critical value. So let us take a look at our t-table. This was a one-sided test, so we do look for alpha. So our alpha value was 0.05, and now we're going to get degrees of freedom as close to 36 as possible. But as I suspected, we don't have 36 exactly in this table, but we do have 35. So we'll use that because it's closer. And so we will use a critical value of 1.6896. So going back to our slides, we have 1.6896. So if we compare, our t statistic was 2.03, and it is indeed greater than our critical value. So therefore, we can go ahead and reject our null hypothesis. So therefore, we can move on to step 4 and say that at the 5% significance level, there is sufficient evidence that the mean SSHA score for females is greater than mean SSHA score for males. Excellent. So there we go. We are at the end of our first example. Now we can safely move on to example 2. We have a random sample of 31 females representing a population of females and a random sample of 47 males, group 2, representing a population of males. We have the IQ of each subject. Is there a difference on average between the population mean IQ scores of males and females? Let alpha be 10%, and in this case, we will assume unequal population variances. Looking at our sample statistics, once again, we can see that our standard deviations are of the sample, and so this brings us down to case 2 or 3. We were told to assume unequal population variances, and so therefore, we need to assume case 3, where we have unequal population variances and known sample standard deviations or sample variances. And so to define our parameters, we're going to let mu1 be the population mean IQ for females and let mu2 be the population mean IQ for males. It doesn't matter how you define your mu1 or mu2. You could have done males first. I tend to do it in the order that the problem has them written. So if males are written in first, then I would have been males, but since in my summary statistics table, females were written first, I tend to just label that as mu1. It is fine, regardless, you will get the same statistics at the end. Your test statistic if you did females minus males, you're doing 105 minus 110, so your test statistic's going to be negative. If you did males first, it would be 110 minus 105. Your test statistic is positive. Since this is the two-sided case, it particularly doesn't matter. The only difference is that your test statistic may be positive or negative. So like I said, personal preference. And if it is a one-sided test, you can still make mu1 or mu2, whichever one you prefer, just make sure the sign goes in the appropriate direction. So if it's saying that males are greater than females, then make sure that sign is pointed in a way that the male population would have the greater than. So now we can go ahead and check our assumptions since we have established our parameters. Our hypothesis test, as I stated, it's the two-sided alternative. So we were told that each sample was a random sample. We're going to assume our samples are independent. Generally, this isn't a problem. And like I said, we'll go ahead and assume it. We'll check our normality assumption by looking at our two QQ plots. Once again, are they perfect? No, but this is real world data, so it's unlikely to be perfect. And so we're going to say that it is normal enough. And now we can actually begin our calculations. So as you know by now, I like to write out what we already know at the top of the screen. So we know our sample 1 has a sample size of 31, a sample mean of 105.83871, and a sample standard deviation of 14.271409. Our sample 2 has a sample size of 47, a sample mean of 110.95745, and a sample standard deviation of 12.120693. We were also told that our alpha was at the 10% level. And since this is the two-sided test, we do need to know that alpha over 2 is 0.05. Last thing I want to write out is our hypothesis that we did already establish. So the null hypothesis is mu1 minus mu2 equals to 0. And the alternative is mu1 minus mu2 not equal to 0. Now we can begin calculating our test statistic. And this is going to be our sample means divided by the square root of our sample 1 sample variance divided by sample 1 sample size plus our sample 2 variance over our sample 2 sample size. And so this will be 105.83871 minus 110.95745 all over the square root of 14.271409 squared over 31. Do pay attention whether or not you're given sample standard deviation and sample variance. You do not want to make I don't want to say silly mistake, but a pretty easy to make mistake that will result in incorrect statistics. Plus 12.12063 squared over 47. and this will give us a test statistic of negative 1.64. And again, I know I said it before, if you had decided to make group 1 males, group 2 females, your test statistic, the only difference was your test statistic would have been positive 1.64. Okay, so because this is our case 3, our degrees of freedom are a rather large calculation. So let's do that now before we move on to step 3. That way we have it established that our alpha level is 0.05, or rather alpha over 2 is 0.05, and our degrees of freedom. So the calculation for the numerator, this is going to be 14.271409 squared all over 31 plus 12.120693 squared over 47, and the whole numerator is then squared, all divided by, let's see, 14.271409 divided by 31, quantity squared, all divided by 31 minus 1, plus the quantity of 12.120693, squared over 47, squared all over 47 minus 1. So very complicated, and if you type this into your calculator correctly, you should get 56.93, which we will round to be 57. So now we can move on to our third step, and that is that we will reject our null hypothesis if the absolute value of t is greater than t alpha over 2. We established t alpha over 2 was 0.05, and that we have degrees of freedom equal to 57. So let's exit out of here and take a look at our t-table. And so third column, and as close as we can to get to 57, which in this case is going to be 55. And so we are going to have a critical value of 1.6730. So it is approximately equal, whoops, the daisies. There we go. Approximately equal to 1.6730. And so in comparison, this would be 1.64, because the absolute value of negative 1.64 is positive 1.64. And as we can see, it is not greater than. So therefore, we will fail to reject our null hypothesis. I do understand some of you might feel a bit uncomfortable because we did do an approximate critical value, and this is pretty close. Just so you know, I myself was uncomfortable, so I did do a double check and checked out the p-value, and the p-value would be 0.1057. And remember, our alpha level was at the 10% level, so strictly speaking, the p-value would be greater than alpha, and we would fail to reject the null hypothesis. And so in this case, the decision was very close. If we had done an alpha level of 0.05, then we would have rejected the null hypothesis. So close, but as they say, no cigar in this case. So at the 10% significance level, and this is important to note because as I just said, if it had been the 5% significance level, this would have been a different case. At the 10% significance level, there is insufficient evidence that the mean IQ score differs for males and females. Excellent. So that brings us to the end of our second example. We can now move on to our third example. After that, we're going to move on to talk about confidence intervals. So for our third example, Bakery A in a small town sells a traditional hot chocolate. However, in the month of February, a second bakery, we'll call this Bakery B, is selling European hot chocolate. Determine if sales for European hot chocolate perform less than the sales of traditional hot chocolate. We will assume that the variances for each population has been calculated, and we are going to use the alpha level at the 1% level. And so let us start by beginning to define our parameters. I'm going to let mu1 be our population mean sales for bakery A and let the population 2 be the population mean sales for bakery B. Notice when I wrote out the hypothesis, I used subscripts A and B. That's perfectly fine if you decide to change your subscripts to reflect different cases. A lot of sample problems you will use like group A and B or group 1 and 2. So if you change your subscripts in reflection of that, that's perfectly okay. Even if it was talking when we did our male and female group, if you wanted to do mu M and mu F to help recognize the difference between the two groups, I'm also okay with that. Just make sure you're using it consistently and correctly. And so they were trying to establish if the sales for European hot chocolate performed less than the traditional hot chocolate. So they were saying that the European was less than the traditional. And I established that the traditional was group 1, and so that's why I have the greater than symbol instead of the less than. You could have equally done our bakery B minus our bakery A is less than 0. Both are correct. Just make sure you're setting up the problem correctly based on what has been stated. And so now we're at the point where we can check our assumptions. So we do have that each sample is a random sample. We are going to assume that our samples are independently collected, and we are checking the normality assumption, and they both look fine in my opinion. In fact, they are probably the closest to normality we've really seen of our 3 examples. So now we can begin with our calculations. I want to emphasize we were given an alpha level of 0.01. We were given a sample 1 sample size of 28, a sample mean of 20.39, and a population variance for the bakery of 20.914. And for sample 2, we have a sample size of 30, a sample mean of 17.84, and a population variance for population 2 of 40.47. We've established that our null hypothesis is mu A minus mu B equal to 0, and the alternative is mu A minus mu B is greater than 0. And so at this point, we can go ahead, calculate our test statistic, which would be Z equals 20.39 minus 17.84. We weren't told about any established difference, so we can leave it at that. All over the square root of 20.914 over 28 plus 40.47 over 30. By plugging this into our calculators, we would get a Z statistic of 1.76. At this point, we can move on to step 3, where we will reject our null hypothesis. And we have been doing lots of our critical region methods, so I'm going to do the p-value for this problem. if our p-value is less than or equal to alpha, which is again at the 1% level. And so because this was the greater than case, we know our p-value is equal to the probability of z being greater than or equal to our test statistic of 1.76, which because of our z-table, we have to find the probability of 1 minus the probability of z less than or equal to 1.76. So at this point, I'm going to close this out and pull up our z-table. And this is the one-sided test. And we are going to want to find as close as we can to 1.76, which shouldn't be a problem. So 1.76 will give us the probability of z less than 1.76 is 0.9608. And so this is going to give us a p-value of 0.0392, which in this case, this means our p-value is greater than alpha. So therefore, we must fail to reject the null hypothesis. And so we will say that at the 1% significance level, there is insufficient evidence that the mean sales of bakery B perform less than bakery A. And it did mention about being in November. So I'd have to go back and read the problem, which I'm honestly not going to do at this point because I don't want to make this video any longer than it needs to be, whether we were talking specifically about the month of November population only. But I'm assuming from what I understood of the problem that basically these bakeries sold the same thing all year round except for the month of February. And so it was seeing if that 1 month different sales made a difference in overall mean sales, in which case we have insufficient evidence of that. So I'm going to leave it as it is. But if you feel I'm wrong, please let me know and I can change things for the future. Okay, so now at this point, this does bring us to our second objective, and that's to construct confidence intervals for our differences in the population means mu1 minus mu2. Now, just as there was before, we do have the 3 different cases. I'm going to go through them relatively quickly and then do 3 examples. And so just a brief recall, what is a confidence interval? A confidence interval is a range of reasonable values for a parameter. A sample mean is a point estimate for mu. Confidence interval for mu is a range of reasonable values for mu centered at the sample mean. And the sample mean plus or minus a margin of error is what constitutes our confidence interval. So when we are comparing 2 population means, we pull a sample 1 that comes from population 1 and a sample 2 that comes from population 2. And so our new parameter is mu1 minus mu2, which implies that our new point estimate will be the sample mean from sample 1 minus the sample mean from sample 2. And so in constructing a confidence interval for mu1 minus mu2 and how we can part of our interpretation for this. If the confidence interval contains 0, we can understand that the two population means are not that different or insignificantly different. So to state that more clearly, because I realized I was thinking multiple thoughts as I was making that statement, if the confidence interval contains 0, then we cannot say the two population means are different, meaning it is the equivalent of the two-sided test where we conclude that we fail to reject the null hypothesis and there's insufficient evidence of difference. That's what we're saying. Saying it one more time for clarity. So when the confidence interval contains 0, that means that there is insufficient difference between our two population means. If the confidence interval does not contain 0, that means we do have sufficient evidence that the two population means are significantly different. Furthermore, if our confidence interval is strictly positive, that means population 1 is significantly greater than population 2, and the reverse is also true if the confidence interval is strictly negative. And so let us take a look at the actual construction of our confidence interval. So we do still follow the form of that point estimate being plus or minus the margin of error. We've established that our point estimate is going to be the sample mean of sample 1 minus the sample mean of sample 2. The only thing that does change is our 3 different options for the margin of error, which is established based on our knowledge of the population variance or lack thereof, and whether or not we assume these population variances are equivalent or not. And so for case 1, when we are actually aware of the population variances, our confidence interval is our point estimate plus or minus z alpha over 2 multiplied by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. In case 2, where our population variances are unknown but assumed to be equal, we do have to make an application of our sample, our pooled variance statistic. And so our confidence interval will be our point estimate plus or minus t alpha over 2 multiplied by the square root of our pooled variance multiplied by the quantity of 1 over n1 plus 1 over n2. We have established earlier what our pooled variance statistic is. This t alpha over 2 critical value must be found by the t distribution with degrees of freedom equal to n1 plus n2 minus 2. And then finally, for our third case where we have unknown but assumed unequal population variances, our confidence interval will be our point estimate plus or minus t alpha over 2 multiplied by the square root of our sample variance from sample 1 over n1 plus our sample variance from sample 2 over n2. Again, t alpha over 2 must be found using the t distribution with the degrees of freedom of that wonderful, very complicated to calculate statistic. And so at this point, we have established our 3 confidence intervals. And so now let's take a look at 3 examples, and then that will be the end of this lecture. So for example 1, a study was conducted in which 2 types of engines, A and B, were compared. Gas mileage in miles per gallon was measured. 50 experiments were conducted using engine type A, and 75 experiments were conducted using engine type B. The gasoline used and other conditions were held constant. The average gas mileage was 36 miles per gallon for engine A and 42 miles per gallon for engine B. We'd like to find a 96% confidence interval for mu B minus mu A, assuming that we're comparing our engines A and B type. We will assume the population standard deviation for engine type A is 6, and the population standard deviation for engine type B is equal to 8. Now, as we were given the population variances, this implies that this is case 1. So we will use the formula of our point estimate plus or minus z alpha over 2 multiplied by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And as we were given that this was a 96% confidence level, this will imply that our alpha level is at the 0.05. And so we will need a z-score such that the probability of z greater than z is equal to 0.02. And so using our z-table, that's going to mean that our z alpha over 2 is equal to 2.05. So let's take a moment and just double check that value. So again, we've established that our alpha is 0.04, and that means our alpha over 2 is 0.02. And as you know, my preference is to look up the 0.02 and then just realize I can drop the negative. So I want to get as close as possible to 0.02. And that looks like it's going to be between 0.0202 and 0.0197. So that'd be 2.0 and between 0.05 and 0.06. So it is a little bit closer to 0.05, so that is what we've gone with. And so now it's just a matter of plugging and chugging. And so our sample from engine type B was 42. Our sample mean from engine type A was 36. We have our Z alpha over 2, 2.05, and then we were also given our sample sizes and our population variances. And so if we plug in, we will get 6 plus or minus 2.57. And so we may establish that the 96% confidence interval for mu B minus mu A is 3.43 to 8.57. Always put the lesser value on the left and the greater value on the right. And so this leads us to, of course, write our interpretation as always. We are 96% confident that the difference in the average miles per gallon for engine type B and the average miles per gallon type for engine type A is somewhere between 3.43 and 8.57 miles per gallon. And if you had done type A minus type B, you would still get the same results. The only difference is if you had done A minus B, your confidence interval would have been negative 8.57 to negative 3.43. Now let's take a look at example 2. The following data represents the length of time and days to recovery for patients randomly treated for one of 2 medications to clear up severe bladder infections. For medication 1, we were given a sample size, sample mean, and sample variance of 16, 19, and 1.8 respectively. And for medication 2, we were given once again, sample size, sample mean, and sample variance of 14, 17, and 1.5 respectively. We want to find a 99% confidence interval for the difference, mu1 minus mu2, in the mean recovery times for the 2 medications. Assume normal populations with equal variances. So we were not given the population variance, but we were told to assume they were equal. So this means we are going to be using case 2, and therefore the formula of our sample mean subtracted from each other plus or minus T alpha over 2 multiplied by our pooled variance multiplied by the quantity of 1 over n1 plus 1 over n2. And we've already established many times what our pooled variance statistic is and our degrees of freedom. So let's get calculating. And so first off, finding our critical value, we want 99% confidence, which means alpha is going to be 0.01 and alpha over 2 is going to be 0.005. And as we have established, we're using the t distribution with degrees of freedom, n1 plus n2 minus 2. And so this will be 16 plus 14 minus 2. And this is going to give us 28 degrees of freedom. Using our t-table, this would give us a critical value of 2.763. Now, before we can plug and chug, we do need to calculate our pooled variance statistic. Plugging in our corresponding values, we'll get a pooled variance of 1.6607. And so now at this point, all we need to do is calculate our confidence interval. So this will be the quantity of 19 minus 17 and quantity plus or minus 2.763, all multiplied by the square root of 1.6607 multiplied by the quantity of 1 over 16 plus 1 over 14 and quantity. This will become 2 plus or minus 1.30. And so this will be a 99% confidence interval for mu1 minus mu2 of 0.7 to 3.30. Stated properly, we are 99% confident that the difference in average length of time to recovery using medication 1 and the average length of time to recovery using medication 2 is somewhere between 0.7 and 3.30 days. Now we can examine our third case, our example 3. Now we're going to use the exact same values as example 2, but in this case we're not going to assume the population variances are equivalent, making this a case 3. And the reason I did want to do this is I wanted to kind of show you the differences between assuming the population variances are equivalent and not. And so because this is the third case, our formula is going to be our point estimate plus or minus T alpha over 2 multiplied by the square root of our sample variance from sample 1 over N1 plus our sample variance of sample 2 over N2. And the truly difficult part of this is calculating the degrees of freedom. And so by plugging into the long complicated formula, we get 27.9373, which will round to have a degrees of freedom of 28. And so now at this point, we can establish that we need to find our critical value. Now, if you do recall from example 2, we are using 99% confidence intervals, so that means our alpha over 2 is 0.005. We got the same degrees of freedom of 28, so we do actually get to use that same critical value of 2.763. And so that's all going to be the same. What's really going to be different is the standard error calculation, which if we plug and chug, we have the quantity of 19.17 plus or minus 2.763 multiplied by the square root of 1.8 over 16 plus 1.5 over 14. And what is this going to give us? 2 plus or minus 1.29. And so with 99% confidence, our confidence interval goes from 0.71 to 3.29. If you recall, in our example 3, or excuse me, in our example 2, it was 0.7 to 3.30, so it has just altered a little bit. And so what we can say properly is that we are 99% confident the difference in average length of time to recovery using medication 1 and the average length of time to recovery using medication 2 is somewhere between 0.71 and 3.29 days. Okay, so this does bring us almost to the end of this lecture. Real quick, what are the assumptions we need for the confidence interval? Well, we need to have 2 populations, 2 independent random samples, and we do need to assume that these populations are normally distributed, and we may use the central limit theorem if our sample sizes are sufficiently large enough. And so what do we need to do for this week? We need to read chapter 5, the first 2 sections. Make sure it is just the first 2 sections. I may have changed the original course calendar, so it is just sections 1 and 2, and I'd like you to complete knowledge check 5. As always, if you have questions, shoot me an email. Otherwise, have a good night.